Yeah, welcome back, everybody. So it's my pleasure to introduce the first speaker of the after lunch session, Yossi Azar. Yossi is a professor at Tel Aviv University and one of the sort of leading lights of online algorithms. He's had numerous sort of important and exciting results. And today he's going to tell us about a line of work he's been pursuing of late of online algorithms with time windows, and in particular, list update. So all yours, yes.
Okay, thank you. So first of all, as everyone else, I would like to thank the organizers for inviting me. It's a great pleasure. And since it's after lunch talk, so I guess that the people are tired. So just ask me many questions, and then maybe you will be less tired. Maybe I'll be less tired. So okay, so I'm actually going to, since it's after lunch, I'm going to focus on a single problem. So you only need to remember one single problem, very simple one, and this update with time windows. So let me first of all remind you what is the list update problem. It's a very simple one. You have a list of items, and you get requests for these items. So we have a list of n ordered items, and you get a request. And they arrive one after the other. Once you get a request, you need to access the element. And your cost is the position in the list. Then after you access the element, you can move this element towards the head of the list. And you can also pay, this is done for free. And you can also exchange two consecutive elements at the cost of one. So the whole idea is actually to minimize the total cost, which I'll show in the next slide. And the only thing that you can do during this algorithm is to move elements towards the head of the list for free, if you access them, or if you want to exchange two elements by consecutive elements in a cost of one. So this is a very simple algorithm. It's a very simple problem. And now, of course, the algorithm task, the goal, okay, what is to be done here is actually to decide how to move the elements in order to minimize the cost. For example, if you would get requested the last element again and again and again and again, so it makes sense to move it to be the first, because you will pay 1 instead of n, because it's the position in the list. And of course, we are talking about online algorithms. An online algorithm, you get requests one by one. You don't see the whole set of requests in advance. So for a given sequence of requests, we called opt sigma, the cost of the optimal algorithm, that knows the whole set of requests in advance and plans what to do precisely. And it can do many things. That after every request, it can switch several elements. It can move the requested elements towards the head of the list or to the middle of the list or whatever it wants, and so forth. And the competitive algorithm is called an algorithm called C competitive if the cost is C times the optimum. So this is like the classical thing. So let me take there is a simple, well-known algorithm which is called move to front, which let's say that you get a request of 8. So after you pay 8 because this is where it is, and you move it to the front. Now you get 5. Again, you pay 5 and you move it to the front, and so forth. This is move to the front heuristic, very simple heuristic. And surprisingly, Slater and Tarjan in seminal paper in '84, actually one of the first papers on online algorithms, proved that this simple algorithm is too competitive against any optimal algorithm that can do whatever it wants during the algorithm. So it's at that time, it was very surprising that such a simple algorithm is too competitive to unrestricted optimum algorithm. So it's very nice. And there is an easy deterministic lower bound of 2. It's a lower bound for online algorithm. Yeah. Then there is a sequence of work about randomized algorithm. You can get it to 1.6, and the lower bound is 1.500 something, about just slightly above 1.5. And there are many other works. So I only summarize the the best results. So there are like tens of papers about this simple, basic, fundamental problem. Okay, so actually this problem is almost solved. So what should we do about it? What can be done about it? So let me tell you, let me take an example. Let's say that you get requests to the last n over 2 elements. So, okay, so let's say that you get them one by one. So how much you are going to pay? So you're going to pay approximately theta of n squared, whatever you do, because you get each one, you need to access, it doesn't matter what you do, you need to access it in the second half of the list, and you pay omega of n, and then totally we get omega of n squared. Any algorithm, including FTF, will pay omega of n squared. But what if we are not required to serve a request immediately upon arrival? So let's say that we can actually serve all the requests together. Then then in one pass, we can actually serve all the requests. Update, let's say, every time that we access an element, we update something. We can update all the n over 2 elements in one pass and pay only n. So there is a huge difference, quadratic difference, n versus n squared in the optimum in the total cost. So that motivates the following problem: list update with time windows. That we are not required to serve request immediately. So we get set of requests. Each request is for some element, but it has a time window. The time window starts when the request arrives, and there is a deadline. And you don't need to serve a request immediately. You need to serve it up to its deadline in its time window. And as I mentioned before, an algorithm now may serve multiple requests together, not at once. And of course, what's the cost? So the excess cost is the position of the farthest element which is accessed. Obviously, you just go through the list and serve them all. And the advantage is that, as you can see here, you as well as the optimum, if the windows overlap. Here we have an example of five sets, of 5 type of requests, and each one we have its window. So this is the time axis. And obviously, we can, if certain requests overlap in time, they can be served together. So very simple. Okay. Obviously, the problem of immediate serving a request is a special case when the time window is a single point. If the time window is a single point, then it's a generalization of the previous problem. Okay, so all this line work about time windows and more generally penalty, which I'm not going to discuss at all, has a lot of previous work. But since I promised you that I'm going to talk only on a single problem, I'm just going to just list several names that worked about this thing, and some of them here. For example, Anupam Gupta, Demalia Panigrai, Ashish Chiplunkar, and I probably pronounced all these names. Although one of them I work a lot, one of them was a postdoc. I pronounced the names incorrectly, so I'm sorry. But yeah, so there are many, and probably you might find yourself here as well. Okay, but I'm not going to explain all these different works because I want, after lunch, we want to focus on a single problem. Okay, great. So we are back to our problem, list update. Not sure if I should use here the, okay, do you see the, okay. So we have the list update. So as you recall, in the original problem, there are free swaps. If you access an element, you're allowed to move it to the head of the list for free. Here we access several elements, so it's not clear how to define what is a free swap. So it's more natural for us actually to define a model that there are no free swaps, there are not free swaps. So model 2, there are not, like in model 1, if you access an element, the swaps are free swaps are allowed, pay swaps are always allowed. In the second model, everything is paid swapped, and the only difference is a factor of 2, because once you access an element, you can bring it to the head of the list and just double the price. So the only difference is a factor of 2. Of course, we are not going to allow accessing 7 elements and moving all of them for free to the end of the list. This doesn't make sense. So since it's only a factor of 2, we are going to assume that all swaps are paid. There are no free swaps, but that's only increase the competitive ratio by a factor of 2, so I'm going to ignore this. Okay, so what's the main decision here? So let's say that I have a request I that I need to serve, and the question is what else should I serve? So if J is very close to I, although J is still, its time window is still it's still not over, I'm going probably to serve it, but here if J is very far, I'm not going to do that. So this is what the algorithm has to decide, and if to serve I and J together when the deadline of I arrived. And the natural definition is to define a trigger element. And now I want to describe an algorithm. So what is a trigger element? A trigger element is, okay, at a certain time, an element which its deadline has arrived. The thing is that several elements might have the same deadline, although this is it's not a big deal. And if several elements have the same deadline, so the trigger element is the farthest one. And so this is a trigger element, of course. And now our algorithm is very simple. It's the most natural one. Let's say that at certain time, all the red elements reach their deadline. I is the farthest one. So obviously, you're going to serve all of them together, including the blue ones here, because all the way to the one you're going to do it, but you might go a little bit farther away. And the question is how much to go farther away. So you choose the simplest thing. If X is the triggering elements of the position, then you just go, you double the distance and serve the request. And what you also do is you move these elements to the front. I mean, yeah, the question is which element to move to the front. The right one is to move the trigger element. Okay, and there is only one result in this paper. This algorithm is 31 competitive. So please note that without time windows, it was too competitive. Here, we worked hard to show that it's constant competitive. 31 is not tight, as you might figure out. If we will, I mean, we probably can reduce the 31 to high 20s if we work hard, but we are far away from I'll mention it later, far away from the low bound. Okay, so I hope that the algorithm is clear, the problem is clear. If you have questions, please ask them now, because this is, as I mentioned, it's one problem, one algorithm. Okay. Yes. Or pending request. Yeah, if on the way you always serve all pending requests because there is no point in leaving them there. I mean, that's the most natural thing. The only question is, there are two questions. How far to go behind the element and which element to move to the front, because you have multiple options. So you move the one which was the trigger one. Okay. So in order to explain the proof, I'm going to remind you the proof of Slater and Tarjan. It's relatively simple. Many of you saw it already, so I'll do it fast, but some of you might not. Yes? The same element, it could be requested many times, sure. The same element, otherwise it's a simple problem. I mean, the assumption is that the sequence is bounded, the list is bounded, it has 100 elements, but the sequence is infinite, is infinite length. So each element repeats itself many, many, many times in different times, yeah, okay? Yes? Again? When you access them together, you serve all the requests. No, I mean, it's a real data structure. You just go over the list, and every time that you encounter a request, you just serve it immediately. And you pay only the farthest element because you just go over the list. It's the simplest, it's a linked list, just a linked list. When you go over the linked list, you just pay exactly the amount that you go on the linked list, and you serve all the requests during. Okay, yeah, I mean, there's no point to have pending two requests to the same element at the same time, because when you serve a first one, you also serve a second one at the same time. So you have at most, I mean, this is what I showed in this example. I mean, there's no point to have the request for a single item are disjoint, because if they overlap, when you serve the first one, you also serve the second one. But in general, it could be arbitrary, but that's. Okay, so I'll show move to front is too competitive. The idea is to use a potential function, but first of all, we have to define the distance between two sequences. So let's say, not sequences, but two lists. Let's say that one list is 1, 2, 3, 4, 5, and the second one is 2, 5, 3, 1, 4. It's the list, it's not a sequence of requests. So the distance is defined the number of pairs I and j, that in one of them, in the optimum algorithm, I before j, and the online is j before I. This is the this is the distance. So like here, if we have 5 elements, 5 of them are inverted. 1 and 2 are inverted. 1 and 3 are inverted. Let's say 1 and 4 are not inverted. In both cases, 4 is after 1. So just the number of pairs that are inverted. And to prove this, we define a potential function. This is a very standard method in online algorithms, which is the number of inverted pairs. And what is proved is that move to front plus the potential function is at most twice opt. It's a stronger lemma, it's a stronger theorem, which help you that it's easier to prove. And since the potential function is always non-negative, you get immediately that the algorithm is too competitive. And actually, you prove something stronger. At every step, the cost of the move to front plus the cost of changing the potential is most twice the cost of the changing the potential of opt. This is completely classical method in online algorithms. And since the potential starts with 0 and at the end is non-negative, when you sum up all these equations, for overall request, you get immediately the required goal, which is MTF is smaller than twice opt. Okay, so I hope that many of you know that because this is completely standard. Okay, and how do you do that? So it's very simple. Let's say you consider a specific request. What's the problem? The problem that opt pays a little bit, y, and the MTF, the online algorithm, pays a lot, x, which means that the online algorithm paid much more. However, in such a case, you improve when you move after xing the element, you move it to the front, and then you improve at least x minus 1 pairs, including the excess element, and you decrease at most y elements are becoming worse. I mean, they change the order. It means that the potential function is improved by at least x minus y, decreases and increases by at most y. Because if you look at this element, so here is after many elements, and here it's not after, it's only after few elements. But when you move it to the front, then it's the number of pairs that it participates that are wrong or correct order or wrong order improve significantly. So the whole idea is that the algorithm pays x, the optimum pays y. The potential function is increased by y by decreased by the x minus y, which is overall it's 2x minus y. And then that's the whole proof. the cost of the online algorithm is x, the change in potential function is 2y minus x, so it's 2y, and that's 2opt. It's very simple proof to a very fundamental seminal paper of Slater and Tarjan. That's it. Of course, there is now something that I ignored. What if opt performs swap? Because in this case, I assume that opt didn't perform a swaps. So if it's a paid swaps, then the potential can increase by 1, and the optimum pays 1, which is fine. And free elements only improve the potential, because if the optimum moves its element to the head of the list, it's only decreasing the potential, so it's fine. So this is something very standard, very simple. Only if opt, since the online algorithm has the element at the front, if the optimum move it towards the front, it only improves the situation. The potential is only decreasing. Okay, so this is it. And now we want to show that our algorithm is 31 competitive. So here we need several lemmas. One of them, we can assume without loss of generality that all requests are triggers. I remind you what is a trigger. A trigger is an element which reaches its deadline and is farthest in these elements. And the reason is that if the adversary removes the non-trigger request from the sequence, then the algorithm actually doesn't notice that, because it behaves completely the same. Just behaves completely the same, while the optimum only decreases, may only decrease. And therefore, you can just get rid of trigger element. I remind you, trigger element is an element that reaches its deadline and is farthest if several of them reach together. So obviously, all requests are trigger elements. And now the second lemma says that during the algorithm, when you get a request, which is obviously a trigger element, its position in the list remains unchanged until it is served. So the position of the element, okay, once you get a request, it's going to be a triggered element. Its position doesn't change until it is served. And what's the reason? It's also a very simple lemma. If you access a request which is in front of the trigger element, you're going just to move this element here, so the position here remains the same, doesn't change. And if you access this element and you want to move it to the front, so in that way, it means that you already served this request. It means that this is not a trigger request. So this is the whole proof. Like, so the position of an element, once it is requested, remains the same until it is served. Okay. So now, if xk is the position of the request ek during its time interval, okay, we denote by xk its position and yk the position of the optimum algorithm for a certain request. It's very easy to bound the cost of the online algorithm. The cost of the online algorithm is very simple. Once you get a request, you move x, you move additional x because you double the distance, and you take these elements and move it to the front. This is why you pay 3x for each such request. So if you have k requests, we just pay 3 times the sigma of xk. Xk is the kth request. Just pay the distance, 3 times the distance of the request from the head of the list. Yeah, because you go twice. I remind you what's the algorithm. You go twice the position of the request, and you move the trigger element to the front of the list. So it's obviously 3x. Is it clear? Okay. I hope it's clear, because this is like the simple thing. And now, let's say that there are several requests which are alive at the same time. E1, E2, and E3 are requests which are alive at the same time. They aren't served yet. Every request is served only at its deadline. So they're alive together. So I want to bound the number of requests, not only the number, but I want to get some some understanding about requests that are alive at the same time. So obviously, let's say if we have such a request and they are all trigger elements, it must be that E1 is served first, E2 is served second, and E3 is served third, because otherwise, and the deadline is if E1 is first, E2 is second, and E3 is third, because otherwise one of them would not be a trigger element. If E2 were the first, then at that time you would serve E1, and E1 was not a trigger element. But we know also, and we know by our algorithm, that the position at least doubles every time, because every time that we serve a request, we go double the distance. And since when we serve the E1, we didn't serve E2, it means that its distance is at least double the second one, and so forth. In particular, we have at most log n trigger elements. And Optimum may serve all these requests together. This is like, in the way that we reduce the problem, the algorithm, since we removed all non-triggered elements, notice that the algorithm serves each request separately, while the optimum may serve multiple requests together. And the multiple requests must be alive at the same time. So this is actually giving you, this is the time zone of the optimum and the algorithm. The algorithm serves B1, request B1, B2, B3, and so forth. And it serves each one separately, because they were all trigger elements, because we get rid of all non-trigger elements. However, the optimum may serve several of them together. B1, B2, and B3 are served together, B3 and B4 served together, and B5 is served by itself. Notice that the optimum must serve the request at the time of the first request. So it must be among the red, it must be the first, and among the green, it must be the first, and this one by itself. So it must be the first, because we serve every request only at its deadline. And since opt served them all three together, it cannot serve it later than B1. So it means that it's always true that the optimum is in front of the algorithm in this way. Okay, and this is actually the main complication of the proof. The main complication of the proof, in contrast to the original problem, in the original problem, they both serve at any point of time the exactly set of requests. And here, it's different, because opt served part of it, and the algorithm served other part. And as we can see now here, opt serves always more than the algorithm. So we need to have this definition of lambda t, which is the set of requests that served by opt, but not yet served by the algorithm. And this will be used in the new potential function that we use. So now it's the most complicated slide. Sorry for that, I know it's after lunch, but still. So now we need a potential function that consists of three parts. And I'm going to explain, hopefully, if I left time and if you will not suffer too much, why we need each part of this potential function. So the potential function consists of three parts. It consists of the original part, which is the distance between the two lists. This is actually what's used by Slater and Tarjan. It's how many pairs are in the opposite order between the algorithm and the optimum. This is the first part. Just the number of pairs I and j. I is before j in alg, and j before I in opt. At certain time, the potential function is defined on the time. The second one is a bit strange, and I'll explain what it is. For x and y, we have something which is okay. This is the picture. Here, y is fixed, and I look at it as a function of x. So it's going up and then going down, going up at a rate of 7, and going down at a rate of 1. And this is only sum up over the request. This is sum up of the current position. This is sum up over all the requests which were served by opt but not yet served by the algorithm. And the third part, which I'll show why we need it, is actually the number of swaps that the optimum has done from the time that he served the request until the algorithm served the request for each specific request. So we are only summing up over the requests which optimum already served and the algorithm not. And between that time, how many swaps the optimum algorithm has done. And I'll try to give you a taste why we need each one of these three parts. Okay? Question about it? I know that this might be seems complicated, but it's very simple three parts of a potential function. Okay. I'll continue. I hope that it's fine. Okay, I'll show you in a minute. I'll try. I mean, the whole proof, more or less, I'm a little bit cheating, but the whole proof is on the slides. Up to some. Okay, so this is the whole potential function and the explanation of each part. So now the proof sketch. The proof sketch is when you use potential function, you always do the same thing. You look at the moves of the algorithm and the moves of opt. So I'm going to see what happens when the algorithm serves a trigger request and opt. Now for opt, I'm going to divide it into cases. Opt perform a swap, because opt also allowed to perform swap, and opt serve multiple requests. So I just need to analyze each movement by itself. When the algorithm acts and the optimum acts for a specific request. This is it, and I want to show that the potential function remains correct at any such movement. And I'm going to show that the cost of the online algorithm plus the cost of plus the difference in the potential is at most 31 times opt. Okay, and as we know, if we prove that, then we get a 31 competitive algorithm. Okay, so now I'm going to see what happens when the algorithm serves a request. And actually, I need to divide it into three cases. The first case is that opt is very, very efficient. It's yk. Algorithm is very far away. It's xk. So the algorithm pays a lot compared to the optimum. Surprisingly, this is an easy case because the first part of the potential function, which is the Slater and Tarjan potential function, the distance between the two sequences, pays for this cost. Okay, the second one is going to be 0, and the third one is going to be 0. And what we need to show that the cost of the algorithm plus the cost of potential function is at most 31 of the opt. Opt pays 0 because opt didn't do anything. So we just need to show that the cost of the online algorithm, as I mentioned, is 3 times xk, because every time it pays 3 times xk because it doubles the distance and moves xk to the beginning. Plus, I need to show that the potential function is at most 0, and I only look at that part because these two parts are going to be, this is going to be 0 and 0. And actually, since y is much, much larger than x, it just go through this. I mean, this is just equation is trivial, it's immediate. So somehow the case where the algorithm pays a lot is actually supposedly in the proof quite easy. Now we look at the middle case. And now we are in that range. We are in that range that x is not so far away compared to y, but not very close to y. So we are in this range of this function that I remind you, this function is increasing at a rate of 7 and decreasing at a rate of 1 until this is for fixed y as a function of x. So here it's x equal y. So in this case, actually, the potential function here is not enough it cannot recover the cost of the online algorithm. But fortunately, in this case, we actually use the second term. This is why we need it. And the second term, we are in that range, is designed in such a way that it exactly covers the cost of the online algorithm. I'm not going to do the math, but this is exactly how it was designed. The third case is this part. Again, this is actually supposedly an easy case because the algorithm pays much less than opt. I mean, this is like supposed to be very easy. Of course, it's not so easy because the potential functions are changing. And again, in this case, the second term, I remind you, every time that the algorithm serves a request, it's becoming closer to opt because optimum is always before, the algorithm is always behind the optimum. So one term of this potential function disappears. And again, if it is designed precisely in such a way that it covers the cost of opt. And okay, and then there was some cheating because I assumed that from the time that the optimum server request until the time that the algorithm server request, optimum didn't move this element. But it might have to move this element, and this is why we need the third part. This is why we need the third part. Since the algorithm may move, there is a time period between the time that the algorithm server request until the optimum server request. This is actually the main issue. It didn't appear previously. Previously, they both serve the same set of requests, and here it's not. And for that, we have the potential, the last term of a potential function that covers this part, this problematic case. Okay, and okay, now I'm switching to the optimum. If optimum makes a swap, then it's actually easy. I'm not going to describe it. This is an easy case. This is at most 1. This is at most 1. We need to prove that this is at most 31. We actually have a slack here. We already know that it's less than 8. This is an easy case. I'm not going to explain it. Oops. Now I'm getting to the heart of the proof. This is actually where the problems appears. An opt server multiple request. Yeah, so this is, I mean, when optimum server request is serve several requests together. So, okay. So if, let's say that he access an element at a position Z, so he pays delta opt is Z. So we need to show that the potential function does not increase by more than 31Z. And what happens when optimum server request? This doesn't change at all because it doesn't change the list. This doesn't change at all. So we need to show that the potential, that this part of a potential function does not increase by more than 31Z, where Z is a cost of the optimum algorithm. And this is a tricky part because now optimum serve multiple requests together. And now we need to solve some optimization problem where, okay, as I mentioned, this part of potential function is 0. This part of potential function is 0. This is going to increase because the optimum now is serving a request. And this is exactly the potential function of a request that were served by algorithm, by opt, but not yet by the request. So this increasing significantly. And the idea is actually, this is here where we need to put a potential function because the optimum, this is where we use this nice picture. Optimum serves several requests together, which are lines here. And we need to sum up the height of these lines. And we know that the difference between the lines is at least factor of 2. So we don't know how to solve this question, this problem precisely, but we know how to solve it here separately and here separately. And the solution for each one separately is easy. I mean, we just lose additional 2. This is why eventually we get 31, because we lose every time some number. And it's not very hard to prove that the location of the request will increase the potential function by maximum if we start, okay, to this direction, we start from here and go by a factor of 2. And for this direction, again, we start from here, we count it twice and go by a factor of 2 to this direction. It's a simple, relatively simple optimization problem, and we serve it, and that's finish the proof. So, okay, I didn't really give the whole details, but this is actually the whole, outline of the proof. I gave you the full outline of the proof. There are some details to fill, but it's like it's interesting because at the beginning we actually had a little bit more complicated proof that show a log n competitive algorithm, and eventually we simplified it and I got a constant 31. So let me summarize. We define this problem because MTF is very efficient in the terms that it's too competitive, but the cost of serving the request may be very high. This is why we want to define problems with time windows. We pull 31. As I said, if we really were trying, maybe we could get to 27, 28, but we didn't bother. It's still in the high 20s. Open problems. Okay, the low bound. Surprisingly, I mean, this is really amazing. We couldn't prove a low bound larger than 2. The same trivial low bound of the single of Slater and Tarjan that you just serve each request immediately. Okay, we can show that our algorithm is not going to be 2. It's going to be at least, I don't remember, 6 or 5 or something. But we don't even know a counterexample for our algorithm, which is above 5 or 6. And we don't know a lower bound, which is better than 2. So there is a still huge gap. Okay, a minor issue here. We don't, I mean, I mentioned there are time windows, but actually we don't need to know the time window in advance. Our algorithm is non-clairvoyant. I didn't want to confuse you at the beginning. We actually need to know the end of the time window only when it ends. We don't need to know it in advance. The question if we would know it in advance. We don't use it in the algorithm, knowing the time window in advance. The question if it could help. Randomization. Would randomization help? Probably yes, but I'm not sure how. And okay, this is the time window. There is a generalization which is called delay. And I don't want to confuse you, so I'm not going to describe it precisely, but time window is hard deadline. You need to serve it in the window. When you have a delay, it's a smooth deadline. But as long, if you serve it later and later, the penalty becoming larger and larger. Of course, it includes in particular deadlines, and this is a more general problem. And surprisingly, we don't know an algorithm for it's actually, we were sure that our algorithm, some versions of our algorithm would extend to the penalty version, the delay version, the penalty version. But every variant that we tried probably at least 5 or 6 or 7 variants. We found a counterexample to them. It's more complicated. That's it. Just on time. Yes. Yeah, otherwise it will be 4 actually. Yeah, so this is also surprising. People didn't look at it so much, but yeah, even for the original problem, I mean, this is what we figure out. If you don't have free swaps, the upper bound is 4 and the low bound is 2. I think that people didn't bother to look at it. Yeah, so it's open. Mm-hmm. I'm not sure, but maybe. Mm-hmm. I mean, surprisingly, one can show that it's a bit counterintuitive. the optimum does not gain nothing from free swaps. I mean, it seems the opposite, counterintuitive. The optimum, it's always better for him to do paid swap. I mean, actually, there is a paper that shows that optimum does not need to use free swaps. It can always use paid swaps and server requests. So free swaps only helps the algorithm. But it means that it will be better, but I don't know how to show it for our case. This was for original problem. I don't know if it works here. Yes.
Does the problem get easier if you have uniform time windows?
Uniform time windows.
That's a special case of the Claire.
Yeah, I understand. I'm not sure.
Like size 2 or something.
Yeah, maybe becoming simpler. I need to think about it. Yes, it's a good question.